I know what you're thinking. I fit logistic regression to my data, but now what? How do I make sense of it? What do the parameters of the threshold actually mean? The answer to this question depends on whether you're using logistic regression to model probabilities or if you're simply interested in its predictive power as a classification tool. Brace yourselves, for this is how I think about logistic regression. Part 3. You may have noticed that logistic regression is actually doing two things at the same time. Not only does it try to classify points as belonging to one of possibly many classes, it also assigns probabilities to the entire space in which our data lives. Some applications are inherently random, and logistic regression is a tool to help navigate and characterize that randomness by assigning probabilities. Other applications aren't random, and logistic regression's probabilities are just a means to an end of trying to find what distinguishes each class from the others. For example, consider a dataset of weights in tons of rhinos in purple and elephants in blue. We would like to know for a given weight whether this is a rhino or an elephant. From the data, we can see that if an animal weighs 1 ton, it's definitely a rhino, and if an animal weighs 8 tons, it's definitely an elephant. But there's overlap between the weights of both animals, so for many weights, we can't know for sure if it's that of a rhino or that of an elephant. So for a given weight, conveying the probability of being one animal or the other is a better description of reality than trying to claim for certain which animal this is, probabilities which we hope logistic regression can model accurately. If instead we were trying to distinguish rats from elephants using only their weight, there would be no need for probabilities. No elephant can weigh as little as a rat, and no rat can weigh as much as an elephant. Since we can completely determine from a given weight which animal this is, there's no randomness and thus no need for probabilities. In this case, using logistic regression to assign probabilities where they're not needed is misleading, but we can still use logistic regression as a classification tool to find what distinguishes rats from elephants. In this case, the values assigned by logistic regression aren't so much probabilities anymore as they are scores which help us make predictions. Depending on whether you're interested in modeling probabilities or simply finding what distinguishes data points from each other, drastically changes how to reason about and interpret logistic regression. So let's take this one step at a time. This is how I think about logistic regression, from a probabilistic perspective. Let's go back to rhinos and elephants. Data science tools, like logistic regression, make educated guesses of what we don't know. So in order to understand its pitfalls, compromises, and power, let's pretend for a minute that we know everything we need to know about the data. Let's say the weights of elephants follows a normal distribution with mean 7 and standard deviation 1, and the weights of rhinos follows a normal 3-1 distribution. Let's also assume that there are as many rhinos as elephants in the wild. Thus, the overall distribution from which our data was drawn is 1/2 the normal distribution of rhinos plus 1/2 the normal distribution of elephants. We can now compute, not estimate, the probability that a given weight is that of a rhino or that of an elephant. For example, let's say that the animal's weight is 5.3 tons. The probability of being an elephant, given the weight 5.3 tons, is the following conditional probability. Using Bayes' rule and plugging in the values and PDFs we know to be true gives us a probability of 0.77, a probability that can be extremely misleading without the context with which it was derived. This probability does not mean that any animal weighing 5.3 tons has a 77% chance of being an elephant. This probability means that out of all rhinos and elephants weighing 5.3 tons, 77% are expected to be elephants and 23% are expected to be rhinos. If we compute this conditional probability for all weights, not just 5.3 tons, we can plot the probability that any given weight is that of an elephant, which you'll notice looks a lot like the sigmoid function. And just like the sigmoid function, it represents the proportion of elephants we can expect at each given weight. But just like the sigmoid function, it can assign very high probabilities to points that are clearly outliers, uncharacteristic of elephants or rhinos. For example, according to this curve, the following animal, weighing just a couple hundred grams, is definitely a rhino, which is confusing because there cannot exist a rhino or elephant weighing this little. This is because this probability expresses that it's much more likely that this animal is a rhino rather than an elephant, even though this animal is definitely neither. Knowing the distribution of the data and evaluating the PDF at this value, we can see just how uncharacteristic it is for a rhino or elephant to weigh this little, which can further contextualize this probability. But in practice, it's near impossible to know the exact distribution of the data, especially when there are many factors that could all depend on one another. Other tools, like naive Bayes, for example, make assumptions about the distribution. Logistic regression tries to bypass the need to know the overall distribution of the data and directly estimates the conditional probability with the sigmoid function simply because of its shape. But if we don't know the distribution of the data, how can we know if the sigmoid function is a good estimate of the true conditional probability? With a large enough dataset, we can divide up the range of weights into a number of bins and compare the observed proportion of elephants in each bin with the probabilities assigned by the sigmoid function. But using the sigmoid function also implies that our data has certain characteristics which aren't necessarily present. Recall from part 2 of this series that by using the sigmoid function to model probabilities, the probability of being an elephant is proportional to the probability of being a rhino, which means the ratio of these probabilities, also called the odds, grows exponentially the farther the animal's weight is from the threshold. Taking the natural log of both sides of the equation, we see that using the sigmoid function implicitly assumes that the log odds grow linearly with the animal's weight. So one way to interpret the parameters of the threshold in logistic regression is as exponential inflations to the odds or additive increases to the log odds. For example, we could say that an animal that weighs 1 ton more increases its odds of being an elephant over being a rhino by a factor of e to the w. Talking about odds instead of probabilities is hugely beneficial in that it draws explicit attention to the context with which these probabilities were obtained. It makes it clear that we're talking about probabilities exclusively in the context of elephants and rhinos, and this interpretability is one of the main reasons why logistic regression is so popular. But are the log odds always linearly related to the factors? Well, since we know the distribution of the data, we can actually compute the log odds to see if they are indeed linearly related to the factors. The probability of x factors out, and we're left with each of the individual animal weight distributions, which we know are normal distributions. Simplifying everything, we see that indeed the log odds are a linear function of the weights of rhinos and elephants. But this is actually only the case because the standard deviations for rhinos and elephants were equal. If they weren't, we would have a quadratic relationship between the log odds and the weights of rhinos and elephants. And in this case, logistic regression wouldn't be appropriate. In practice, though, we don't know the distribution of the data, and determining whether the log odds are or aren't linearly related to the factors is very challenging. To recap, logistic regression models the randomness of belonging to one of possibly many classes given some factors. No randomness, no need to model probabilities. But these probabilities can be misleading by themselves as they don't explicitly convey the context with which they were derived. Talking about odds instead draws attention to that context and can mitigate some confusion. Both odds and log odds are central to logistic regression as the use of the sigmoid function implies that the log odds are linearly related to the factors, which may not always be the case. Most of the time, however, logistic regression is used for its predictive power. In this case, the values assigned by logistic regression aren't so much probabilities anymore as they are scores which help us make predictions. But if we can't interpret these values as probabilities, how do we then make sense of logistic regression's parameters of the threshold? This is how I think about logistic regression from a machine learning perspective. If you're only interested in the predictive power of logistic regression, it's important to understand that the data is being warped toward a specific goal. Understanding the mechanics of that transformation can help us relate logistic regression to many other machine learning tools. Over the course of this series, we learned that carefully changing the parameters of the threshold in logistic regression helps us mold the sigmoid function to our data. But we can also see it as molding our data to the sigmoid function. Let's go back to our data set of people's ages and whether or not they can legally drink. Notice that this isn't a probabilistic problem since there's no overlap between those who can legally drink and those who can't. Let's zoom out a bit. The sigmoid function, as written, doesn't quite fit. That's because the sigmoid function is centered around a threshold of 0 and our dataset is not. So we shift the data before it goes into the sigmoid function. Exactly how much we need to shift the data in order for it to be properly centered around 0 is something gradient descent will learn iteratively. By properly centered, I mean that all people who can't legally drink should be on the left side of the threshold and all people who can should be on the right side. In this case, a constant of -21 captures the data well, separating around 0 those who can legally drink from those who can't. But logistic regression doesn't stop there. We want probabilities that make the data as likely as possible. By increasing the magnitude of the values that go into the sigmoid function, we generate more extreme probabilities, which can improve the likelihood. We can do this by scaling the data. Notice that we're adjusting the amount by which the data is shifted as we scale in order to keep things properly centered. A function that shifts and scales in this way is called a linear function. When we have three classes, we need three of these linear functions to mold the data to the softmax function. Recall that with two classes, we plotted where that linear function was 0, and that was the threshold that separated the classes. If we do the same with three classes, we realize that these linear functions are no longer the boundaries between classes. So if we can't think of these linear functions as boundaries, what are they? Well, if we think of these linear functions as transformations that shift and scale our data, we can think of each of these linear functions as mapping our data to the real line in a unique way. Let's take a closer look and see exactly what each linear function is doing to our data at each step in the gradient descent process. Notice that some points are mapped to positive values and some to negative values. The positive ones are assigned a probability closer to 1 by the softmax function, and the negative ones a probability closer to 0. With three linear functions, we hope that each one will discover a unique way to transform the data so that only points unique to a specific class are mapped to positive values. Depending on how we scale and shift the data, we'll assign better or worse probabilities to our space, which will change how well the softmax function fits to the data we saw. So we can think of logistic regression as trying to find the best ways to scale and shift the data in order to mold it to the softmax function. This perspective of molding the data to the specific model is, in my opinion, a hugely beneficial way to approach data science because people are too often focused on the model and not enough on the data. But data science is all about the data and what information is extractable from it. Practically, though, shifting and scaling is hardly sufficient to extract information. For example, if the data is two concentric circles, there's no way to linearly transform the data so that points in purple are positive and points in blue are negative. Of course, there's always the option to modify the data yourself to add more factors you think or know to be relevant to the task. But this is an arduous process that tools like neural networks try to automate. With this perspective, tools like support vector machines or neural networks become natural variations of logistic regression. We'll be talking about those soon. To recap, the parameters of logistic regression in the context of machine learning can be thought of as scaling and shifting the data with the goal of molding it to the sigmoid or softmax functions. Only scaling and shifting limits the kind of information that is extracted because of how little the data can be warped toward that end. I hope this helped you better understand logistic regression. Like, subscribe, and help me spread this knowledge around if you found it helpful.